All right, let's welcome our next group. The muxes. Sounds like the band or something. Yeah.
All right, let's get started.
All right, so why are muxes important? A multiplexer is a combinational circuit that has many data inputs and a single output that depends on control or select inputs. Muxes are mainly used to increase the amount of data that can be sent over the network within a certain amount of time and bandwidth. Multiplexers are used to select either a register operand, which is a 0, or a constant operand, which is a 1. So instructions that muxes support: a multiplexer is a logic gate circuit used to fetch a bit of data from memory at a given memory address. A processor has several multiplexers controlling the data and address buses. Multiplexers are switches allowing the processor to select data from multiple data sources. To select which data source should be used, a multiplexer has one or more control lines, also known as selectors, and the output of a multiplexer is the selected data.
So as we have up here are multiple ways you can create your mux. Yeah. I mean, simple as that. You can have NANDs, you can have two ANDs and an OR. We always have our NOT gates so that we can select stuff. There, super easy. For our test cases, as plain to see right here. Wow, I really wish those showed up properly.
So what did you test, or why did you test those?
So there were two ways that we had. They could test it. On the right is Mark's, on the left is mine. On my side, I tested whenever it hit the negative edge of the clock, it would select different values. This is our 5-bit mux. So in this case, it was 5 zeros all over for A, B, and our output would end up being would be 0. And I essentially just tried to extend that truth table to how we tested it out. For Mark's, he chose what times they were selected, and this music is killing me right now. No, keep it going.
No.
For the meme. For the meme.
For the meme.
Basically,
It is pretty good. Wait, how many grocery stores?
there's 14 of them or something. It's a full album.
Buy this album?
No, it's on YouTube. Why would I need to buy it? I can just go on YouTube. No.
Okay, so hold on a second here. So on the second one, you're selecting input 0, and input 0's input is 0, so the output should be 0.
It should be 0.
Yes.
So,
but your box is a 1.
is it the one on the right over here? This test case you're talking about?
He's talking about the truth table.
Oh, I didn't know there was text there.
Yeah.
So I'm looking at the box.
The truth table.
The truth table?
So that
The table of
that's
truth?
not the truth table that I had up there before.
Dun.
You guys change it?
No.
Okay.
So you
Cool.
just say it's wrong, and instead it should say...
That's wrong. It should say 1 instead. It should say 0 instead. My bad. I can't speak. I'm still thinking about that wonderful music that's going on just now. So yeah. Basically, truth table wrong. I'll fix that. I did. Bring it up.
So some issues with implementing muxes. In the first one is going to be overall when you go to implement it into your processor. If you're not careful with bringing all these components together and doing them right, you'll get an unexpected X value, even though it was working by itself, because you've got a bunch of moving parts coming together, and if you mislabel one or have two of the same variable name, it won't know what to do, and that'll cause an issue. But moving back to implementing just the mux, if you mislabel, say you label the register a wire, or the other way around, or you just miss that part entirely, it'll tell you that you're trying to use a register that doesn't exist because you never told it that what you're trying to use is a register. And then other errors are going to come from misspellings, not using the right number values, or missing entire key lines of code.
Awesome. So we implemented this in structural style. So you code up each like it's an individual 2x1 mux. So that means the gate delay is 5. But as you can see from my lovely hand-drawn picture here, I went all out for you guys. They run in parallel. Awesome. So your gate delay is still going to be 5 because each of them's output does not depend on the other. Awesome. So that means it's 5. And the 64-bit is much the same. I did not fully draw out all 64 of the 2x1s because I'm not doing that. And so I just drew the one big one so you can see how it all comes together. But again, everything works in parallel, so it's still 5. Yeah. And that's it.
All right, any questions? I haven't heard any questions from back here.
Oh, he's got a question. We got one over here.
Oh,
Is the real Sammy T and the Muxes going on tour?
I am totally down for that.
We're only going to play supermarket music.
You can hear us in your local Publix and or Walmart neighborhood market.
Yeah.
Fantastic.
Only the neighborhood
That was a
market.
good one. I did not
wow. I wonder how well that
Yes,
picked
Sam.
up on the.
How did you pick the music?
How did I pick the music? Unfortunately, my friends and I have a weird sense of humor, so occasionally in our Discord, calls, we will have a moment where we're in the middle of a very intense game, and then somebody will just throw this up in our playlist, and all of a sudden, an intense firefight will become supermarket music. That's it.
Although in Verilog, when the system is coded and the muxes are running in parallel, you basically consider the delay to be 5 because they're all working together.
Right.
However, when it is physically implemented as an actual computer chip or module,
Right,
do
right.
you think there might be additional delays that could come from that?
Oh, absolutely, because you're going to have your branching out costs, as Dr. West has said during the lectures. You're going to have fan out costs. Sorry. Let me get my terminology right before I quote you. Sorry.
Making sure we're all on the same page.
Yeah, you have your fan out costs, so that's going to be a lot more delay, and then you might have to end up adding more saturation because you might lose power as you go out, so that'll add additional delay as well. So.
So hold on. We talked about the muxes. We talked about the different types. Did y'all put up a diagram of the processor and where the muxes are and which one's which?
No.
Nope.
Nope.
Sure did. Okay, so the mux that selects which register is going to be how many bits?
That's your 5-bit, yeah.
Yeah, that one's
5-bit,
probably
yeah.
good. And the mux that feeds an input to the ALU.
That's 64.
Correct. And then the mux that sends the output to the program counter.
That is, I believe that's also 64.
Yeah, we'll go with 64, sure, or 32.
Yeah,
depending on which way you
depending,
wanna-
yeah.
Which way you decide to rate up your processor. And I think that's oh, there is one more mux going into the register file. That's the data. But that's coming after the, data going to the register file. And so that one's going to be, yes,
64.
64, okay, great.
Right.
Good, just want to make sure we're on the
Yes.
same page.
Yep.
All right, good job. That was too much.